All right, our next topic then is dealing with these quantum numbers that I referred to in the last unit, which aided us in so much that we can now write an electron configuration. I used to teach this first and then electron configuration second, but this is much more complex. Electron configurations I showed you in 10 minutes, and you were able to write an electron configuration. And based on the results of our last test, you got it. It was a pretty simple concept. You were able to interpret the pattern on the periodic table and come up with the electron configurations for an element. This is the background to it. So now that you understand what SPs, Ds, and Fs and where they are on the periodic table, this stems. All right, so we did talk about Schrodinger and the fact that Schrodinger wrote a mathematical equation which expresses the location of an electron around the nucleus based upon probability. And the magic number is 90%. 90% of the time, we're going to find the electron in a particular location. All right, so let me jump right in. The probable location of an electron is defined by, we're simplifying things here, but basically we're solving Schrodinger's equation and coming up with these values. And we refer to them as quantum numbers. All right, so the principal quantum number is designated with the letter n, sometimes capital N, but usually a lowercase n. It represents the energy level. Now, we've already discussed how we have a very general description of where the electron is called an energy level. Energy levels are made up of sublevels. Sublevels are made up of orbitals. And then inside the orbital, which is two electrons, one is spinning one way and one is spinning in the opposite direction. Well, this is the first of those. So the first one is called the principal quantum number, letter n. And it defines the size of the electron cloud. Now, the allowed values, again, referring back to the solutions to Schrodinger's equation, the allowed values for n are 1, 2, 3, 4, ... 7 right now on the periodic table, but in theory, all the way to infinity. So whole numbers, starting with 1 and working their way up, are the allowed values for energy level. We can use the principal quantum number to know how many electrons there are in an energy level by using the formula 2n squared. Now, this is something that we already know. If n equals 3, so n equals 3, that means it's in the third energy level on the periodic table. We know that there are s's, because there's 3s, there's p's, 3p, and there's d's, 3d. So s, p's, and d's. Well, we also know that s's can hold 2, p's can hold 6, and d's can hold 10. So if we were to count all that up, we would say there are 18 electrons in the third energy level. Well, 2n squared tells us, 3 squared is 9 times 2 is 18 electrons. And that will work for any value all the way up to infinity. So we can figure out how many possible electrons there are. So therefore, it dictates the size of the cloud, because the higher the energy level, the more electrons, the larger the electron cloud. All right, so the second quantum number, and we usually abbreviate that like so instead of the other one looks like a 1. So lowercase l or capital L, and this is sublevels. So energy level made up of sublevels. Right now in the periodic table, we know there are SPs, Ds, and Fs because we can write an electron configuration. All right, the allowable values for L are 0 to n minus 1. 0 to n minus 1 are the allowable values that, again, plug into Schrodinger's equation, solving to figure out this position of the electron. These are the allowable values. So that means, going back to the third energy level, if n equals 3, L can equal 0 to n minus 1, so 0 to 2. So we show that by going 0, 1, and 2. Now, these correspond to the labels S, P, and D. Let's go back to, let's say, n equals 6. All right, so if n equals 6, or in the sixth energy level, L equals 0 to n minus 1, so 0 to 5. These correspond to S, P, D, F, and if you recall from there, we start going alphabetical. Now, they didn't choose A, B, C, and D to make your life easy, and where they came from was, remember what we talked about right before Schrodinger's equation? We had Bohr's model of the atom, and Bohr did spectroscopy, so he studied line spectrum, which is what we're going to talk about in class tomorrow. And 4 of the words used to describe lines in a line spectrum are sharp, principal, diffuse, and fundamental. So it sort of pays homage to Bohr and his work. All right, so it also will tell us the shape of a sublevel. So solving Schrodinger's equation, we get this electron density map, the electron cloud, and where the electron, once again, the magic number is 90% of the time. And graphing that in the x, y, z coordinates, you get a particular shape. And the S sublevel is a spherical shape. And 1s would be smaller than 2s, so 2s would be bigger, more electrons. 2n squared, so there's 2 electrons in the 1s. There's 2 electrons also in the 2s, but overall it's going to be a larger shape. So P is equal to a dumbbell shape. So S is spherical. P, we usually draw it at 2 dimensions to look like that. But I think this picture sums it up a little better. Now these coordinates are the x, y, z coordinates, x and y being what we know. The z is going to come out 90 degrees from the board from those. And so we can't draw that in 3 dimensions. And so it's normally drawn like that, but this is really rotated so that you could see the 3 axes. If you turned it back that way, the line that I drew would be coming straight at me 90 degrees from the other 2. So here's a nice picture of that electron density, if you can try to imagine that, and they try to make it look 3-dimensional by shading that. Same thing here, and same thing there. And if you recall, when we did our orbital notation, we had S's and P's, and remember, they were referred to as Px, Py, and Pz. Well, this would be Px along the x-axis, this would be Py along the y-axis, and this would be Pz along the z-axis, although chemists and physicists normally put the z-axis as where we would normally put the y. Just some more pictures. Once again, if n equals 1. Well, if n equals 1, L equals 0. 0 corresponds to the S, and so there's the 1s. There is no 1p because there are no allowable values for L equals 1 when you have n equals 1. When n equals 2, L equals 0 and 1, which corresponds again to S and P. So here's the S, and there's the P, the 2s and the 2py, px, and pz. And the pictures along the y, the z, and the x-axis. Another picture. And just another picture, try to make it look 3-dimensional. All right, so we have S is spherical. The P is dumbbell shaped. The D we call double dumbbell shaped. That was a really pathetic drawing. Like so. Again, the limit of my artistic ability. There we go. So now we see what we're really looking at here are areas of electron density. The S had 1 area. It was just a spherical. The P's have 2 areas of electron density. You can see the D's, and according to these pictures, have 4 areas of electron density. We're going to, if you take advanced chemistry next year, we'll talk about nodes and antinodes and where the electron exists and can't exist. Notice the designations again. They get a little more complicated. We have dx, dy, dxzz, dxy, and then you have x squared minus y squared. And then they have this funky one with this donut shape around the center. Right? And again, this is solving Schrodinger's equation, the possible values. You can see that donut shape a little better on this one. All right, so then the F's. The S are spherical. The P's dumbbell shaped. The D's double dumbbell shaped. Well, the F's, they call it a rosette. And again, it's a simplification of it, but that third dumbbell coming in and out of the board, 3 dimensions. It's not flat, it's not planar, it exists in more than one plane. And again, that's a simplification. You can go see the pictures. There are pictures just like we saw with the D. There's a couple funky ones for the F. And they also, have a letter designation. And then a value in terms of the quantum number. So if n is 4, L is 0, 1, 2, and 3 to n minus 1, S, P, D, and F. So this would be an L value of 0, an L value of 1, an L value of 2, and an L value of 3. So if you had the 5F, we've called that a sublevel. What that really is known as is an orbital designation. So the third of the quantum numbers we'll see in a second. So the orbital designation, well, n is 5 in this, and L would be, so coming back down to here, L is 0, 1, 2, 3, so L is 3. So if it's the 6p, N is 6, L is 1. So that's how you can tell the first two. And that's where we spent most of our time with electron configurations. We did do an orbital notation. So we had energy level made up of sublevels. Now we have sublevels made up of orbitals. And the orbital is a space occupied by 2 electrons. And there, once again, I mentioned, is that 90% probability, solving Schrödinger's equation. This year we usually just call it M. Advanced chemistry next year we get a little more involved with this and we give it another name. But it could also be known as L sub M. So the sublevels showing that it is directly related to the sublevel. The possible values for L sub M or M are negative L to positive L. Let's go back to n equals 3. So n equals 3. L equals 0, 1, and 2, which again correspond to S, P, and D. Now we say when L is 0, M is equal to, well, it's negative 0 to positive 0, so it's just 0. So the fact that there's only one value for the orbital means there's only one orbital when you have the S sublevel. When L equals 1, we already said that's the P. When L equals 1, M would be negative 1 to positive 1. So negative 1, 0, and positive 1. So 3 values for M tell us that there are 3 orbitals, each one holding 2 electrons by definition. So the P's can hold 6. I'm going to come down here. L equals 2. M equals negative 2, negative 1, 0. Positive 1 and positive 2. So negative L to positive L. 5 values for M. 5 orbitals, each one 2 electrons. So 10 electrons total when L equals 2, or the D sublevel. So I think it's, elegantly simplistic, I guess is how I like to describe it. It's you can write an electron configuration, like I said, in 5 minutes, but yet behind all of that is all of this complicated mathematics, which turns out to be pretty simple. All right, so it also defines the direction in space, so which way it's facing. That's what we talk about when we say px, py, and pz, for example. As we already said, that tells us how many orbitals. So the S has 1, the D's have 3. I'm sorry, the P's have 3, the D's have 5, the F's have 7. And then remember, it goes alphabetically, G, H, I. You can kind of predict the pattern there as to how many orbitals it'll have, therefore how many electrons it will have. No idea why that's there. All right, so the fourth quantum number, S or L sub S, remember, lowercase l. And it can only have 2 values. It's either spinning one way or the other, because we're talking now all the way down to the most specific number, which, energy level made up of sublevels. So we had energy level made up of sublevels, and then we have these sublevels made up of orbitals. And now inside of the orbital is going to be 2 electrons, one with one value and one with the other. One spinning one way, one spinning the other. All right, so here's a summary. We have the quantum numbers. And over here we have those formulas that I just showed you. And so what we want to do is write the 4 quantum numbers for the electrons in the oxygen atom. So oxygen on our periodic table is atomic number 8. It doesn't say it has a charge, so we're going to assume it's neutral atom of oxygen. And if it has 8 protons, it has 8 electrons. The electron configuration, 1s2, 2s2, 2p4. We can write that. That's the long way. Helium 2s2, 2p4 would be the shortcut, and I'm going to show you that in a second. But I did want to do this one so I can do all 8 electrons instead of just 6 of them. Okay, so we want to come up with the 4 quantum numbers, N, L, M, and S, or L sub M, L sub S, for each of the 8 electrons in the oxygen atom. So the best thing to do would be to write the electron configuration and then go by the orbital designations. So the 1s, the 2s, and then the 2p. So the 1s is going to have 2 electrons in it, each with its own unique set of 4 quantum numbers. All right, so I like to write the 1s designation on the left-hand side here. So now the energy level. Well, the energy level for both of these comes from the coefficient, so it is in the first energy level. The L, I think the greatest way to solve the L is to write L equals 0, 1, 2, 3, 4, dot, 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 and write the letters that it corresponds to, which are S, P, D, F, G. dot, 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 alphabetical. So if we're in the S sublevel, that corresponds to an L value of 0. Now, according to the formula right here, if m equals negative L to positive L, so if it's 0, it can only be 0, negative 0 to positive 0. And so if you're in the 1s sublevel, that means the first 3 of the 4 quantum numbers are going to be the same. So the last one cannot possibly be the same, or you'd be solving Schrodinger's equation for the same place at the same time, and you can't do that. And so we give one a spin going one way, and then the other one spinning in the opposite direction. What we just did there was a statement of what is known as the Pauli exclusion principle. The Pauli exclusion principle says no 2 electrons can have the same set of 4 quantum numbers. Okay. Next designation, the 2s. And again, I have 2 electrons to put into the 2s sublevel. All right, so now I have n. N is 2, second energy level. L is 0 again. Why? Well, we're in the S. In the S sublevel, remember what I said, the most important thing to write on the top of your paper when you're doing this? L is 0 when it's S. Well, m, negative L to positive L, negative 0 to positive 0. So once again, we're in an S sublevel. First 3 quantum numbers are going to be exactly the same, so the last one must be that opposite spin. And now the 2p. So 2p, we have 4 electrons here that we need to come up with quantum numbers for. This one's a little bit more tricky. More tricky? A little bit trickier. All right, so we have 2 p's and we have 4 electrons. Well, the first of the quantum numbers is simple enough. It's a second energy level. The second quantum number up here again is simple enough. We have the p sublevel, so L is 1. All right, now this is where it gets a little more complicated. And we've already learned the rule that will help us, and it is Hund's rule. Hund's rule, if you recall, said that electrons will fill empty orbits before they pair up. All right, what am I talking about? Remember when we did this? This is the 2p sublevel. We have 4 electrons to put into this 2p sublevel. Hund's rule said they filled empty ones, like so, before they paired up. That's what Hund's rule was. So not only did we fill the empty ones, but we also did something called parallel spin. We had them going all in the same direction before we paired up. Now, if we went all down or all up, it doesn't really matter. They are all equal in energy. The term there is degenerate. They are degenerate. They're equal in energy. But let's translate this into quantum numbers, since we've already done that. If you don't know how to do that, go back and watch the video on orbital notations. All right, so when L is 1, M can be negative 1, 0, and positive 1. So when I do these designations, I'm going to take into consideration Hund's rule and the fact that I want parallel spins with the first 3. So I'm going to say negative 1, 0, and positive 1. And I'm going to make them all spin in the same direction. Okay, so now this last electron, I put it in with the negative 1. But remember what I said about degenerate? Degenerate means it's same equal in energy, so it didn't really matter which one I put it in. But I'll put it in that one. And then the spin, since I already have a negative 1 and a positive a half, I do have to make it go in the opposite direction. All right, so I wrote the 4 quantum numbers for the 8 electrons in the oxygen atom. Let me jump ahead to this one. Now let's do carbon, but let's do the shortcut this time, because that's how we're actually going to do this. We're going to do the shortcut electron configuration, and then we're going to write the 4 quantum numbers for however many electrons we have after the noble gas that we wrote in brackets. And so I'm just going to do it for these 4 electrons right here in the carbon atom. So helium 2s2, 2p2. I want N, L, M, and S, or L sub M and L sub S, however you're learning that. We have the 2 of them in the 2s, and we have 2 in the 2p. So I'll do the 2s ones first. N equals 2. Remember what I said about the most important thing you could write on this to help you with this would be L equals 0, 1, 2, 3, 4, S, P, D, F, G, etc., etc., etc. We have an S sublevel, so L is 0. When L is 0, M is 0. Negative L to positive L, negative 0 to 0. So just 0. And then Pauli exclusion principle. They can't have the same spin if they have the same 3 quantum numbers. All right, the 2p. Once again, we're in the second energy level. All right, once again, I'm going to refer to my chart that I write at the top. And L is 1 because I'm in the p sublevel. So now my choices here are p's have 3, -1, 0, and +1. And remember, Hund's rule, they don't pair up, and they have parallel spins. So my choices there could have been here and here, here and here. Remember, these are degenerate, but I do want to have them spinning in the same direction. All right, so that's the gist of quantum numbers. I have that already. The Aufbau principle we already discussed. That said, electrons will enter orbits of lowest energy first, orbitals of lowest energy first. The easy way to remember that is by the diagonal rule or by the arrangement on the periodic table, going left to right. But we can do the shortcut configuration, so we know that. There's the statement of the Pauli exclusion principle. No 2 electrons can have the same set of quantum numbers. And so, therefore, they all have different electron configurations. And then the last one, Hund's rule, that they will fill each orbital in a sublevel before they pair up. So they fill empty orbits before they pair up. All right, so that's that. So there's quantum numbers.